Okay, so hello everybody. We starting today our lecture with grand canonical ensemble. Okay, so why do I need another ensemble? We already had microcanonical ensemble, and for the microcanonical ensemble, it was difficult, right? So we had an assumption that basically the energy is kept constant, and in order to count our states or our possible states that are accessible for the system, we had to solve usually a very complex combinatorial problem, even for a very simple system. Right? Now, just to remind you, for example, the two-state model. Okay? So if we had to supplement it with additional state, so it would be 3-4-state model, okay? It would be almost impossible to solve it in the way that we actually try to achieve in microcanonical ensembles fashion. How we solve the problem? We relax the condition that the energy is constant, and we basically said the temperature is constant, which also means that the average energy is also constant. Not the energy itself, but the average energy is constant. And there are some fluctuations. Okay? And by allowing for those fluctuations to actually decrease sufficiently fast, okay, what we have achieved is the freedom not to count only one specific states that are accessible for very specific energies, but we count all the possible energies. Okay? Not just one specific state. Now, the same problem may occur when our system is actually depends on numbers of particles. Okay. So, for example, we know if this is our energetic spectrum, and we have several energies. Okay. So we have E1, we have E2, and we have E3. Now, the total energy of the system, or the energy of the state, would depend how many particles are occupying each energetic state, or in general, each state of the system. Okay, so I can assume, well, I have 2 particles at E1, okay, and 1 particle at E3. Okay, so the number of particles per state, per energy, I can call it the occupation number. The total energy of the system depends on various occupation numbers in the system. But the occupation numbers itself are somehow correlated. Why? If the total number of the particle is kept constant, and total number of particles. So if n is kept constant, when I'm counting the possible occupation numbers in order to calculate the total energy, in order to calculate what is the energy of a state. So this is a state. The energy of the state is E1 plus E1 plus E3. But if the total number of the particles is 2, this is already a not accessible state. Why? Because I have 3 particles over here, and the total number of the particles is only 2. I can continue on and on, and I can invent all other different situations, but for each state, each different state, I always have to remember that the total number of particles is constant. So I cannot assume a state that actually has 4 particles here. If the total number of the particles is 2 or 3, it's the energy 4 multiplied by E1 is not an accessible state. I cannot count it in order to describe what is the distribution. So all different energies are accessible from one point of view, from the point of view of the canonical ensemble. But because the total number of the particles is constant, it limits the accessible state. So we have a constraint. The same as we had a constraint with the energy, so only a specific energy was possible. The same goes with number of particles. The number of particles is a constraint. So the number of particles is also can constrain our possible energies. When we are writing e to the minus beta ei, sum of I, and ei I will tell a tilde ei, it's not the specific energies, but the energy of a state, of a specific configuration of all different particles, and I'm summing over all different configurations, I always must remember that I have a specific constraint. And again, I am entering into a combinatorial problem, because I cannot just count everything. The beauty of canonical ensemble is that I just counted all possible energies. I just started, this is the possible energy, this is the possible energy, and I'm just counting over the energies. This was the simplicity of canonical ensemble when compared to the microcanonical ensemble. But when I'm starting to deal with systems that have a constant number of particles, I again encounter this this problem, this combinatorial problem, because I cannot just sum over all different configurations. My space of configurations, a configuration, a specific presence of occupation numbers, my space of configurations is again limited by the constraint. Right? This problem is solved by the grand canonical ensemble. How it's solved? Well, in the same fashion as canonical ensemble appeared, okay, as actually resolving the restrictness of the energy, the grand canonical ensemble basically releases or isn't this restriction of total number of particles. So what we are going to do is basically invent an additional ensemble in order to calculate the statistics of a system, and instead of keeping the total number of the particles constant, what we are going to do is to keep the average number of the particles constant. Okay? So I just remind you how we basically done it for the system. Thank you. So this is our reservoir, the heat bath. Okay. And we're looking on our system, which is much, much smaller than the reservoir. So this is the system. In the microcanonical ensemble, the energy of the system was constant. Okay? And then we replaced the constant energy by a heat bath, so by a reservoir with constant temperature. So T was constant. Now we want to do the same thing, but for the number of particles. Okay? So the associated variable with energy was temperature, and we kept temperature constant. The associated variable with the number of particles is what? The chemical potential. So mu, we're going to keep it constant. Okay. So we're going, instead of keeping n constant, we're going to keep mu constant for the reservoir. Okay, it's now not a heat bath, because it's a bath of particles and it's a bath of heat, temperature. Right? And we're going to allow the system to exchange particles with the heat reservoir. What is kept constant? The energy of the reservoir plus system. So reservoir plus system, energy constant, and number of particles constant. But there are fluctuations in the number of particles for the system. It can exchange energy with the reservoir and it exchange particles with the reservoir. Okay. It's like what I'm saying. I'm looking on this marker and I'm saying, well, the number of particles is actually constant. It's not exchanging any particles with its environment. But if I look closely enough, I would see some fluctuations of the, the particles that are bouncing on top of it or something. There are some small fluctuations of dust or whatever. I can say, well, this distribution is very, very narrow. Well, I don't care. It can be very, very narrow as long as I'm actually allowing for it to be a distributed value instead of a constant value. There is a big difference between a delta function and a very narrow function, as we might learn when we come to stochastic processes. Okay, so what is the ensemble? What are the probabilities to find the system in a specific state, configurational state? Okay, what is the probability? Is how they are obtained in the same way as the canonical probabilities were obtained. So remember what we have done for the canonical ensemble. We define the probabilities for the system to be in a specific configurational state. So Fi, it's the probability of the system to be in a configurational state I. How we define it? The number of states of reservoir that are that satisfy state I of the system, okay, divided by the total number of states of system plus reservoir. So remember, I had dices, and I was playing with dices, and I was saying, well, I have 3 dices. What is the probability of a specific event? And then I had to count all the possible probabilities of all the dices that are contributing to this event. My event was, for example, that the total number should be, or the dices should be 3 or 4 or whatever, or the specific dice. The same goes here. I'm looking. So the number, what is the number of states? I'm looking on the number of states. There's a lot of states that are compliable with a single state for the system, because then reservoir can be in many states. And all those different states of the reservoir should be divided by the total number of states accessible for the whole system. Okay. So this is our basic equation. This is our basic equation, and we should start from here. Now, how you write it? Write it just exactly what is written over here. So Fi equals to omega reservoir for E total. E total is the total energy of the system plus reservoir, minus Ei. Ei is the energy of the configurational state I of the system. And N total, so the total number of particles, minus Ni. So a configurational state of the system Ei is a state when the system energy is Ei and the number of particles in the system is Ni. Okay. All of this should be divided by omega. Omega of what? Let's call it omega total. Okay. So what is omega total? The number of states of the system and their reservoir. And there are no changes, not in the energy. So it has E total and it has N total number of particles. No more and no less the system plus the reservoir is very restricted. All right, what we are going to do next. So for the reservoir, for the system plus the reservoir, so for everything, the entropy, we're still using kb log of omega. Okay, and omega is exponent of 1 over kb of s. So instead of writing the expression for the probability while using the number of states, the omegas, I'm going to use the simple definition of the entropy taken from where? From microcanonical ensemble. Because I'm assuming that everything here is microcanonical. Okay. So what I have here, I have Fi equals exponent of what? Exponent of 1 over K Boltzmann of S reservoir of E total minus EI, and here I have N total minus NI, minus 1 over K Boltzmann S total of E total and N total. Okay. So this is my probability. What I'm going to do next, I'm going to basically expand. The plan is the same way as we have obtained it for canonical ensemble. So what we have done there, we've taken this entropy for the reservoir and we expanded it. Expanded it as a function of what? As a function of fluctuation of the energy around the average energy and the total number of particles around the average number of particles. So before doing this, I just should remind you that S total of E total and N total, it equals to what? It equals to S. S is just, when I'm just writing S, is meaning the entropy of the system, of U and N, okay, plus S of reservoir of E total minus U and N total minus N. Why I'm going to use U is the average energy, U average energy, and N is the average number of particles. So why am I doing this expansion? Well, A, I'm allowed to. Entropy is extensive property, so it's always, entropy is the sum of the entropy of my system and the entropy of the reservoir. So here I'm safe. But why actually doing this, and specifically why doing this with some average energy as some average number of particles? Well, because I want those guys to be constant. This is what I want to be. And eventually I want to express Fj by using what? I want to express Fj as a function of Ej, Nj, and U and N. I want to forget about E total and I want to forget about N total. I wouldn't care about them. What I want to leave actually in the equation, I want to be a function of average energy, because I am assuming it's constant, average number of particles, again I'm assuming it's constant, and the only things that I would care about them. What is this? EI, NI. A specific definition of a configurational state. Because I want to count over all possible states, and each state is going to be defined by the total number of particles in this state. Okay? This is the only quantities that are going to be important to me. So look on the formula. The formula is S reservoir and I have S total. S total, I'm going to use this expression over here in order to transform it into U and M. Okay? Now I'm going to, after I will perform the substitution, I would be still left with E total and N total. And I want to get rid of them. I want to get rid of E total and N total. And you see E total and N total are appearing already here. So what I'm going to do next is basically use this, the entropy of the reservoir, in order to get rid of E total and N total. How I'm going to do this? So let's look what is S reservoir of E total minus EI and N total minus NI. I can write it down in the following way. So it's just simply S reservoir of E total minus U, right? Minus U plus E total minus U plus U minus EI. Okay? And the same trick with N total. So it's N total minus average. Let's write it down over here. I don't have enough space. Equals to S reservoir of E total minus U plus U minus EI. Okay? I added and subtracted U. And the same thing with N total. So N total minus average N plus N total minus NI. That's it. Okay, so this equality is exact because I haven't done anything. I added and subtracted U. The next thing, and this is, well, you might think it's not an exact, I'm going to expand in a Taylor expansion the S reservoir around what? Around E total minus U, N total minus N. Okay? So this actually equals to S reservoir of E total minus U, N total minus average N plus ds dE multiplied by U minus EI plus ds d what? dN multiplied by average N minus NI. Okay, so this is the first order expansion, first order Taylor expansion. Now what I have left, I still have left plus the squared S the E squared multiplied by something plus the squared S the N squared multiplied by something plus the squared S of the E and the N multiplied by something, and I have a lot of different other terms. So basically, well, I need to account all of them in order for this to be exact. But, and this is this lovely trick that we already seen, what is ds dE? What is ds dE? Do you remember? I will remind you. So ds dE was definition of the temperature. So ds dE equals 1 over T. ds dN what equals to what? To minus mu divided by t. Remember what we have assumed. So this is S. This is S of reservoir. Reservoir, reservoir, reservoir everywhere here. So it's reservoir, reservoir, and reservoir. So if this is the temperature, run over the temperature of the reservoir. But the temperature is constant. So the derivative of the entropy of the reservoir with respect to E is constant. What is this guy over here? The derivative of the entropy of the reservoir with respect to the number of particles. This is just the chemical potential divided by the temperature. The chemical potential, we assume it to be constant. The temperature, we also assume it to be constant. This is also constant value. Okay. Now, if those guys are constant, what happens to the second derivative? It just disappears. It's 0. And this guy is killed, and this guy is killed. Because the first derivatives are already constant, so the next derivative, the second order, the third order, the fourth order, they are just 0. So this becomes exact under this assumption that the temperature is constant and the chemical potential is constant. So what I have obtained, I have obtained that S reservoir of E total minus EI and N total minus Ni equals to what? Equals to S reservoir of E total minus U and N total minus average N plus, okay, so what do we have here? Plus 1 over T U minus EI, 1 over T U minus EI, okay, minus mu divided by T, and here I have average N minus Ni. Now I'm ready. Ready for what? Remember, the goal is to compute the probability of the system to be in a configurational state I. This is the equation. It is a function of E total, N total, and all different kinds of particles, values that I don't really interested in counting. But remember what I have already done. So S total I'm going to replace by this equation, and S reservoir E total minus EI, N total minus Ni, I'm going to replace by this equation, and this guy over here, S reservoir E total minus U, N total minus N, is going to cancel out with this term over here. Is the same term. Here it will have a minus sign, and here it's going to have a plus sign. Okay? So what I got rid of everything that had E total and N total inside. What I had left with temperature, constant, chemical potential, constant. Average energy is going to be constant. Average number of particles, constant. Okay? And eventually I'm left with an expression that depends purely on EI and Ni. Okay? So let's write down this expression. We have Fi equals exponent. So by using this and this, we obtain that Fi equals exponent of 1 over K Boltzmann. What I have left inside? I have left inside S U n minus sun. Okay. What else? Plus 1 over t u minus ei minus mu divided by t average n minus ni. Okay, so this is my expression. Let's work it out a little bit more. Let's take into a prefactor everything that is not dependent on ei and ni. We get that fi equals to exponent of minus s of u and average n divided by k Boltzmann plus u beta u, beta, remember what is beta? 1 over k Boltzmann t, okay, du, and minus mu beta of average n. So this is the prefactor, and it's all multiplied by an exponent of minus beta. What I have inside? What I have inside is ei minus mu ni. Now this expression is very similar to the canonical ensemble. Okay, so I have a prefactor which is constant, it's not dependent on I, and I have something exponent of minus beta I will rewrite it over here. So Fi is equals to an exponent of what? An exponent of minus beta psi, this is something constant, multiplied by an exponent of minus beta ei minus mu ni. In a minute I will describe what is this psi over here, but it is constant for us, and the only thing that matters is actually in here, and it's very similar to the canonical ensemble with just very small addition. What is the addition? Minus mu ni. So the energy is shifted by the multiplication of the chemical potential and the total number of particles, and not the total, and the number of particles for this configurational state. So we can count all different configurational states, and they're going to be different by actually entering different numbers of ni. You can say, well, Stas, you started with a system that had 1,000 particles, and now you're counting states that are having 1,000,000 particles. It's not possible. What I would answer to you, well, who knows what's possible, what's not, but for my case, when I'm going to treat a system that had 1,000,000 particles, the probability of this event is going to be extremely small. It's just a multiplication by minus mu and multiplied by 1,000,000. You can say, well, it's negligible. It's negligible, so don't count it. But it's actually much more advantageous to count this in your statistics and use the average properties of the total number of particles and the average properties of the total energy And it's much more simple to do this. It's not about what is right and what is wrong. First of all, we know from quantum perspective that there is no such a thing as certainty. We have an uncertainty principles for the positions of the particles and the energy of the system. Okay? So we can always know that on the very microscopical level, the energy of the system, well, we cannot know the energy of the system. And we cannot know the positions of the particles, and if we don't know the positions of all the particles, we don't know who is exactly on the left side of the boundary or on the right side of the boundary. There are small fluctuations always. And since there are always small fluctuations, and from a mathematical perspective, it's much more easier to take into account those fluctuations instead of assuming constant number of particles, right? We're going to use this ensemble in order to describe our systems with constant number of particles. Now, what is this guy? What is this psi over here? What is this psi? So psi is U minus ds minus mu n. Is it right? Is it right? Yes. So then I will have beta psi over here. Okay. So psi is the grand canonical potential. Grand canonical potential. We'll treat it in a bit. First of all, how I find it now. So this is the potential that describes the different properties of the system. It plays the role of the free energy, of the Helmholtz free energy that we used to in the canonical ensemble. In the grand canonical ensemble, there is a different potential. Instead of Helmholtz free energy, we have U minus ds minus mu n. The thing to notice that it's again a Legendre transformation. And the same Legendre, so as we were using Legendre transformation for the energy, or the entropy, for the entropy in the canonical ensemble, the grand canonical ensemble is a different transformation of the entropy. So the entropy was the potential for the microcanonical ensemble. The free energy was the potential for the canonical ensemble. The grand canonical potential is the potential, or the Legendre transformation of the entropy in order to get fluctuations of the number of particles. And then you can do this trick with any type of property that you want. You want to keep pressure constant everywhere? Well, you can invent your own potential. You want you want to keep some different extensive, no, pressure is not a good example. Well, it actually yes. But if you want to keep some extensive property, for example, not the energy, not the number of particles, a different property that is extensive, and you want to keep it constant or allow fluctuations, you can transform by Legendre transformations to a different representation, to a different potential. So for each ensemble, there is a specific potential, which is always some Legendre transformation of the entropy. Why it's always going from the entropy? Because our starting point was always a microcanonical ensemble. Even here, when we developed everything, we based our assumption on what? We based our assumption that the total number of particles, the total energy is not changing, so we can use the microcanonical ensemble. The only assumption that we ever made about how the system is behaving was only for the microcanonical ensemble. Everything else was developed. How one find this guy? You remember for the free energy in the canonical ensemble, it was just minus 1 over beta log of the partition function. In the same way, we find the grand canonical ensemble, because what we know that sum of I, fi, should be 1. The probability to find the system anywhere should be 1, because it's sitting at one of its possible states, right? So what we have a sum of I, e to the beta psi multiplied by e to the minus beta ei minus mu ni, okay, should be 1. So e to the beta psi, sum of I, e to the minus beta ei minus mu ni, close parenthesis, equals 1. This guy reminds us of something. It's just the partition function. Because what we have done by introducing this additional degree of freedom for the number of particles, we changed the energy here. So this is our new energy. Okay? And then this is just the partition function of the system. Is the partition function for the grand canonical ensemble. So what we see over here, we see that sum of I, e to the minus beta, e of I minus mu ni, let's call it z. This is the partition function, grand canonical ensemble partition function. And what we know that E beta psi of Z equals 1, which says that beta psi is equals to a log of 1 over Z, or psi equals minus 1 over beta log of Z. Again, the moment I know how to compute the partition function, I know how to calculate the grand potential. And the moment I know the grand potential, grand canonical potential, I know everything. This is the state function, remember? This is just the Legendre transformation of the energy, or the free energy. So I can, from this, calculate the entropy, I can calculate average energy, I can calculate Helmholtz free energy, I can calculate enthalpy, whatever I want I can calculate. This is the full class of thermodynamics that you heard, partially from me, partially from somebody else, and you have already done it. Here how those state functions are actually computed for any system. So in thermodynamics, for example, how would we calculate the average energy? Right? How would we calculate the average energy? So there are two ways now how to calculate. One is the thermodynamic way, very, very simple. It's basically to say, well, what is the grand potential? What are our potential? And different derivatives of this potential provide me the different values that I'm interested in calculating. For example, the average energy. But there is also another way which is much more simpler, or much more intuitive. So the first way, the thermodynamic way, of calculating is to say the following. Psi equals U minus Ts minus mu n minus beta psi, So let's look not on psi as a potential, but on this guy. This is going to be our potential. It equals to what? It equals to K Boltzmann S minus beta U plus beta mu N. And now I want to calculate U. What is U? So I know minus beta psi. How I know it? Well, I calculated the partition function. Okay, so I know psi. And I want to calculate U out of this guy over here that I somehow calculated from the microscopical description. The thermodynamic way is, well, to say the following. Look what we have here. So this guy equals to a Legendre transformation of the entropy, K Boltzmann entropy, when entropy was dependent on U and N. So those were the variables, the extensive variables that S was dependent on, U and N. Here is, of course, N, and here is also the average number. Okay. Now, what I have done here, I have performed a Legendre transformation with respect to U and N into new variables. What are those new variables? Beta and beta mu. So instead of having the variables U and average N, I'm having new variables which I obtained by the means of Legendre transformations, and those new variables are beta U, beta mu, and beta. Now, if this is a Legendre transformation, what is U? U is simply the derivative, or derivative of this guy, derivative of minus beta psi, with respect to beta, equals to whatever stands after beta. Because the Legendre transformation is what? Is the original function minus the new variable multiplied by the potential derivative, the derivative of the potential with respect to this variable. Okay, so what stands over here is K Boltzmann S plus beta dou minus beta psi dou beta plus beta mu dou minus beta d minus d beta psi d mu beta. Of course, I have to use beta and beta mu as different variables. So when I'm taking this derivative, what I'm keeping constant is beta mu equals constant. Now, if this is the Legendre transformation, so this is of this form, so beta is multiplied by the derivative that I'm looking for, but I already know what is this derivative looks like. It's just minus u. And I can obtain by taking a proper derivative of this potential with respect to the proper variable. I can obtain here the average energy, and I can obtain here the average number of particles. Okay. I just need to take derivatives. Yes?
For the formula, this should be entropy over KB.
KB S. Why?
Beta is 1 over KB plus.
So it's 1 over KB?
Yeah.
Okay. I'm sorry. Thanks. Minus KB. Yeah. Okay. But actually, it's very boring to compute this derivatives all the time, and a little bit of waste of your well, energy. Why? Because in order to count different properties, it's much more easier, especially if those are average properties, and in thermodynamics we usually have average properties. It's much more easier to do something completely different, but much more natural in our system. Why we are using all of this formalism? Because in thermodynamics we had no probabilities. We had averages. Well, we didn't know that U is average. We said this is the energy of the system, but it was average. We had no way of actually calculating the different probabilities for different energies. By the definition of the average energy, it equals to what? It equals to the sum of all different configurational states of Fi multiplied by Ei. What is Fi? Fi equals to E minus beta Ei minus mu Ni divided by Z. The moment we have Z, the moment we have those values over here, we have everything. We don't need to go compute the ground potential, take derivatives, etc., etc., etc. It's something, sometimes it's common. Why it's common? Because, well, you already know the connection between this ground potential or some enthalpy and magnetic field or whatever. But usually when you have the probabilities and to calculate, for example, the average, you just multiply the different outcomes, so different possible outcomes of your energies by the probability of the energy. You want to calculate the second moment? Well, you compute the probability by the Ei to the second power. You have everything the moment you have Fi's. So if you have the distribution function, and having all the Fi's is actually having the distribution function, you don't need all those ground potentials, etc., etc., etc. You can always work with the original formula. Right? So U would be equals to sum of I, Ei, e to the minus beta, Ei minus mu, and I, all of this divided by Z. If I want to compute the average number of particles, by the way, now I see why U is constant. Look at the formula. Ei's are constant, Ni's are constant, because those are very specific configurational states that I had. What are the parameters? Beta and mu. So if mu is constant, and this was the chemical potential of the reservoir, and the temperature of the reservoir is constant, also the U is constant. The same I can do for the average number of particles. What is the average number of particles? N equals to sum of I, Ni, Fi equals to what? I can calculate this as sum of I, Ni, e to the minus beta Ei minus mu Ni divided by the ground potential function. Partition function, sorry. If I want to calculate the fluctuations, the energetic fluctuations or the particle fluctuations, how I'm going to do this? Well, I can compute the second moment. Compute the second moment, so n squared average should be sum of I, Ni squared, e to the minus beta of Ei minus mu Ni, all of this divided by the partition function. Okay? And the fluctuations, okay, delta of n, I would say this is a square root of n squared average minus n average squared. And it equals to a square root of a sum of I, Ni squared, e to the minus beta Ei minus mu Ni divided by Z minus 1 over Z squared, 1 over Z, I'm sorry, without square, sum of I and I, E minus beta ei minus mu ni. Okay, and the square root goes here, and here the square. Okay. So, moment I have fi's, I have everything. I have the statistics of the system. I can calculate different appropriate variables, etc., etc., etc. The problem is how you compute fi, how you compute the partition function. Where is? How you compute z. The moment you have z, you're basically done. So the whole problem is always to compute z. And now we have the technique to actually do it for a huge number of systems. Why? Because, well, here I have had restrictions on the energy, and I had restrictions on the total number of particles. Maybe I can have a restriction on something else. Well, I would just need to take a different ensemble. I can invent it because now I know how to actually invent those ensembles. I need to invent a different potential, or basically take a different Legendre transformation of my entropy. Okay? And that's it. Then I will have a different not grand canonical, but some ensemble. I can calculate all different FIs, and very simple, right? Well, actually, it's not that simple, because as we will see, it's very difficult to calculate z. So what we have done till now mainly are particles, gaseous particles, gaseous systems, where everything was uncorrelated. Now, even if it's uncorrelated and we have quantum statistics, we have some sort of a different correlations that are penetrating into our system. So to calculate z, it can be quite a difficult task, even for a gaseous system. For example, for fermions, as we will see. Why? Because for fermions, the occupation numbers are always restricted. There is always either 1 or 0 particles per state. And for bosons, it's not like that. But when you have correlations in the system, so for example, this particle can sit over here, or this state is occupied, or this particle in state A, but it also reflects and affects all different particles in the system. So I cannot just count, well, all different states of this guy and all different of that guy because they are not correlated. No, when I'm deciding what is the configurational state, I should use only allowed states. And this is the problem of calculating z. Okay? It's usually what we've been able to do so far, somehow break those correlations and obtain z as a multiplication of different particles. This was always the trick, because we only can calculate z if it's if it's factorizable into different states. But if it's not, we are in a deep problem. So what we are going to do from now is actually to treat z in the grand canonical scheme for fermions and bosons, which we couldn't do it so far because of the restriction of the n. And not this week, but maybe next week we will start to see how we are actually treating correlations. Because most of the systems that we know are not gaseous. There are some interactions. There are some interactions in the system, and those interactions, they make this task of calculating the partition functions very, very difficult. Sometimes it's very, very simple. So for example, in metals, regular metals, we would see that we can treat, even for very low temperatures, the metals as some Fermi fluid or Fermi gas. Okay? So it's basically a non-interacting particles, even for very, very low temperatures, based purely on this assumption of the Fermi statistics. But sometimes it's not the case. And sometimes those electrons in metals that are actually responsible for conduction, okay, they start to interact very, very strongly. And then when interact very strongly due to the media, those interactions can turn them, instead of fermions, into bosons. And then the statistics changes and something else occurs. We'll see how it actually comes into play. So for now, we have additional 5 minutes. For now, I want to start with a simple system. Well, we are deep in the grand canonical ensemble. Oh, yeah, just one last thing about the derivation of Fi. I remember that I had a definition of the entropy of the disorder, which is also an entropy, which is due to Shannon, and it goes like S plus minus KB, sum of I, Fi, log of I. Okay. And I use this guy for the canonical ensemble, in order to say, well, if this is the disorder, this is the entropy, I maximize it, and its maximum, because everything that I know about the system is in equilibrium, at maximum, this was an assumption, at maximum, this disorder should provide me the Fi's which are responsible for the equilibrium. Okay? So I already have done this for the canonical ensemble. In the same fashion as we have calculated the Fi's for the canonical ensemble based on the maximization of this entropy can be performed for the grand canonical ensemble. So what I need to do, this is an alternative derivation. Of grand canonical ensemble. Okay, I should look for delta S equals 0. So I should find the extreme point, which is basically as saying delta of minus K Boltzmann sum of Fi log Fi. It equals to minus KB sum of I. What should I have here? I should have log of Fi plus 1 delta Fi equals 0. So it's the same equation as we had for a canonical ensemble, and I should have restrictions. And my restrictions are that the sum of Fi equals 1. The second restriction is sum of I, Ei, Fi equals U, and this is constant. Okay. And the third restriction of the grand canonical ensemble is that sum of I, Ni, Fi equals average n, also constant. So by solving this equation with those three restrictions, constraints, well, again, I should use Lagrange multipliers using Lagrange multipliers. Okay, I will obtain, and I won't do it because it's exactly similar to the way we already have obtained it for a canonical ensemble. I would obtain that Fi equals to the e to the minus beta Ei minus mu Ni divided by z, and z is simply equals to a sum of I e to the minus beta Ei minus mu Ni. Okay. So again, I can use some thermodynamics and the number of states, or, and it's much more preferable, I can say the entropy always equals to this guy. Always. But there is one thing that I should know about entropy and the equilibrium situation. In equilibrium, the disorder that is described by the entropy is maximal. So what is the way to find Fi's? No matter what are your constraints are, you can always say the entropy is always equals to this. I can always take into account my constraints, and I should find the maxima of S with the constraints, and this will provide me the possible Fi's of the system. Okay. By the way, in thermodynamics, we define the entropy only for an equilibrium. Okay. There was a state, the state was in equilibrium, and we defined the entropy for the equilibrium only. The entropy was not defined by some non-equilibrium process or non-equilibrium state. In Shannon, we define it everywhere, and we just know that an equilibrium, it has a maximum. Okay, this is actually quite interesting. So now we can use entropy for any kind of state, but only for equilibrium what we obtain are those wonderful relations, very specific relations. There is no an analog of maximization of entropy for a non-equilibrium situation. It's a grand open question of non-equilibrium statistical mechanics. Can one find a way to represent the different possible behaviors of the system in a statistical fashion similar to what we have over here? It's not existent so far. Okay, we will. So what we have left with is to finalize this fermion and boson representation of the system, and afterwards, we don't have a lot of time, but still we will have to treat mean field representation and Ising model. I was hoping to get into diffusional processes and stochastic processes, but I don't see that's going to happen. But it's better going slow. Now, so what is about quantum fluids and gases? Basically is treating systems of non-interacting particles which obey either Fermi or Bose statistics. And still non-interaction picture. Why it's called fluid? Well, we will see because especially for fermions, this is a very nice application of this non-interacting particles that are fermions. For example, electrons in metals the electron flow inside the system, but they are completely non-interacting with each other. The interactions that actually happens there, from the perspective of what we will call a Fermi fluid, is the Fermi interaction. So the occupation of different energy level is very specific to the Fermi statistics. This is right. But the particles do not affect each other in any other form. So they cannot occupy the same state. This is correct. But they are not actually somehow repelling each other. We will see how it's possible because if we're talking about electrons, they do repel each other. So how we can assume that in a metal, electrons there do not repel each other and do not interact. This is interesting. Before actually going to the full scale of this problem, I would like to start with something much more simpler and in order to illustrate, because eventually the moment you get the concept, everything becomes simple, and it's easier to describe this constant of quantum gases fluids by using simple systems instead of a very big system or gaseous. So what we have over here, we have, this is our different energies, and we have 3 different energy levels. E1, E2, and E3. Right? The system is Fermi system. And each particle can have plus 1/2 or minus 1/2 spin. Okay. Quantum particles, think about electrons, whatever. Quantum particles spin up or spin down, can occupy energies E1, E2, and 3. No magnetic field. So we will have some sort of a degeneracy. This is why I don't have a magnetic field. So no magnetic field. And no magnetic field. Okay, so what are the possible states of the system? If it's fermions, each energy state can be occupied with either 0 particles Okay? Either 0 particles, so there is no particles whatsoever, or 1 particle with spin up. So different configurations. No particles, nothing. Or 1 particle of spin up, or 1 particle of spin up and 1 particle of spin down. And this goes for each state. Okay. This is the Fermi statistics. No particles or 1 particle. Now, there can be actually 2 particles. Why? Because there is a degeneracy. If I had a magnetic field, external magnetic field, so this state would be actually broken into 2 substates. Okay? Then I will just kill the degeneracy. I wouldn't have an E1 state. I would have E1 plus something and E1 minus something. And this E1 plus something would be occupied with a particle with spin up, 1 particle only, or 0 particles. And the lower state would be occupied by 1 particle with spin down or 0 particles. Now we are talking about the system where there is a degeneracy. So, no magnetic field. Now I want to understand how the system works. What are the different probabilities? What is the equilibrium description of the system? How I'm doing this? Well, I'm calculating the partition function. So this is a sum of Z. That is a sum of over configurational states. Okay. And it equals to the e to the minus beta, and here I would write the energy of a state minus beta, the number of particles that is associated with this configurational state. Now, what is the energy of a specific state? The energy of a specific state is how many particles are occupying energy 1, how many particles are occupying energy 2, and how many particles are occupying energy 3. So let's write it down. Let's write it down. So we have N1 particles. Let's write down. N1, the green, it's not good. So N1 plus, definition, the number of particles in energy in E1 and spin 1/2. So it's Ni plus. And Ni minus. Ni minus is just simply the number of particles in Ei and spin -1/2. Now, in order to say this is a specific configuration, I should say I have N1 plus specific here and N1 minus specific. N1 2 and N1 2 minus. N1 3 plus, N1 N3 minus. So the energy of a specific state, configurational state, is N1 plus N1 minus multiplied by E1. So this is the total number of particles in a system E1. So this is the first contribution to the energy. What else I have? Plus N2 plus N2 minus, is it too small? Can you still see it? Okay. Multiplied by E2. Plus, what is the number of particles in a specific configuration at the third level? So it's n3 plus n3 plus n3 minus multiplied by E3. So this is the energy of a specific configurational state. I haven't specified what are the n1 plus, what are the n minus plus, but if I know what are all the different ni's, I know what is the configuration. I can say, well, I have 2 particles over here, 0 particles over there, and 1 particle over here. So a configuration, a specific configuration. So if I have 1 spin up, 1 spin down over here, a particle will spin up for E2, and a particle of spin down at E3. Okay? For this specific case, this example, I have n1 plus equals 1, n1 minus equals 1, n2 plus equals 0, n2 minus equals 1, n2 plus equals 1, n2 minus equals 0, here spin down, and n3 plus equals 0, and n3 minus equals 1. Okay, this is the example. This is a specific configuration. I should sum up over all the different configurations, all different possible values of n1 and n2 and n3. But this is still not enough. Right? It would be enough, okay, if I was only dealing with what? I was only dealing with a constant number of particles. But then the summation is different, or it's difficult. Why it's difficult? Because when I sum over all different possible values of n1 and n2 and n3, I should also bear in mind, well, the different particles, okay, there should be constraint. What is the constraint? That n1 plus n2 plus n3 plus n1 minus, n2 minus, n3 minus, it's all equals to something very specific. It's difficult to do this. Instead of deciding, well, we have a constant number of particles, we're saying, let's treat the system differently. Let's treat it in a grand canonical representation. And in the grand canonical representation, I say, well, n1 plus and n1 minus and n2 plus, they're complete. I don't care about them. I don't care. They are not correlated with each other. Why? Because the total number of particles can be whatever I like. Then I should only add here minus mu, and here I should write down what? The number of particles that is associated with this specific configurational state. What is the number of particles that are associated with this configurational state? Is simply the number of particles at E1 plus the number of particles at E2 and the number of particles at E3. This is simply n1 plus n1 minus plus n2 plus n2 minus plus n3 plus n3 minus, and I close my parenthesis. That's it. This is my partition function. I just now have to count over all different n1s, n2s, n3s, and n4s. And they are not correlated with each other because I don't care that if n1 is 0, it's not affecting n2. Because the number of the number of particles can fluctuate. Beforehand, if I'm choosing, well, n1 is 0, well, then n2 can be something. But if n1 is 1 and the total number of particles is 1, then n2 should be 0 by definition. Now I don't care about this possibility. So what are the different configurational states? Because the summation here is over all different configurational states. What are the different configurational states? All different values of n1, n2, and n3. n1 plus, n1 minus, etc., etc. But I just need now to count over all different values of my occupation numbers without restriction, without taking into account what are the other values. So when I'm writing down here the configurational states, I should write that Z is equals over sum of N1, N1, N1 goes from 1 plus 0 or 1. N1 minus equals 0 or 1. N2 plus equals 0 or 1, etc., etc., etc. I sum up over all possible values of the n's. What I have over there? Well, I have a multiplication of a lot of guys. So instead of writing this as a big sum, let's split it. How we split it? We say it is e to the minus beta n1 plus e1 minus mu n1. Okay? I can do this. You just separate the sum. Multiplied by e to the minus beta n1 minus e1 minus mu n1 minus. Multiplied by e to the minus beta n2 plus e2 minus mu n2 plus. And just multiplied over all different values. Okay. This I can write as, well, I can sum up because it's a multiplication. I can break down this multiplication into this summation into multiplication of summations. What it breaks down to? Breaks down to sum of n1 plus goes from 0 to 1 of e to the minus beta n1 plus e1 minus mu n1 plus. Multiplied by a sum of n1 minus goes from 0 to 1. It's a non-restricted summation. Beforehand I had a restricted summation, now it's a non-restricted summation of e to the minus beta n1 minus e1 minus mu n1 plus, okay, multiplied by a summation of n2 plus goes from 0 to 1. Why it's 0 and 1? It's a Fermi system. Either one particle or zero particles. E to the minus beta n2 plus e2 minus mu n1 n2 plus. And I have all the additional terms over there. Now look, this term and this term, it's exactly the same, right? It's exactly the same. Why it's the same? Well, the only difference between here and here is that I'm using here n1 plus and here I'm using n minus, n1 minus, but it's a dummy variable. So what do I care how it's called? So let's write down this as z1 1/2 equals to a sum of n. I'm sorry, zij. Let's write it down. What is zij? Zij is a sum of I goes from 0 to 1, e beta n I e I no e I n I e I minus mu n I. Why j? J, so I goes from 0 to 1 and j you're right. So this is j, no, so let's call it, you are right. You are right, so I am sorry, so this is going to be ij, it equals to k, it goes from 0 to 1, kei minus mu k. Okay, so k is a summation, it's a dummy variable, and the I is the definition of the state, so it's ei, and j, so I can be 1, 2, or 3, it defines the state, and j can be 1/2 or -1/2, or plus or minus. So j is the spin, and I is the level, energy level. So what we have over here, we have that z is equals to z1 1/2 multiplied by z1 minus 1/2 multiplied by z2 1/2 multiplied by z2 minus 1/2 multiplied by z3 1/2 multiplied by z3 minus 1/2. This is a factorization. So we started with a simple system, Fermi particles, they are not interacting. There are some sort of interaction because the occupation number are restricted, or either 0 particles per side or 1 particle per side. And we can still break down everything into a multiplication, of different partition functions. Now, what is the small partition function? It's a partition function of a level without any relation to the occupation on the partition functions of other levels. Okay? So I have a lot of levels. My levels are 1 spin up, 1 spin down, 1, 2 spin up, 2 spin down, 3 spin up, 3 spin down. There should be different. Z1 1/2 and Z1 1 minus 1/2 are going to be different if there are different levels, because then the energies in general would depend on I and j. In our system we have a degeneracy, and this degeneracy basically means that Z1 1/2 equals, or Zi 1/2 equals to Zi minus 1/2. So in total, what we got from our description of the system, in total, we obtain that Z is a multiplication of I, Z I 1/2 squared. Why the squared? Because of the degeneracy. And so we just need to go over all different states. Okay? Define what is the partition function of this state. Okay? What is the partition function of this state? What is Z1? What is Z2? What is these 3? And from this, we can calculate everything else. We basically said, well, we have a system of n particles. There's some sort of interaction between the particles. This can be occupied, this can be non-occupied, etc., etc. Eventually, I break down everything to multiplication. What is factorization? What it means, look at one single level and say to me, it's occupied, it's not occupied, what are the probabilities? And that gives you all the answers that you need for the grand system, because afterwards, everything is just a simple multiplication. Why I'm saying this? Well, let's look on one specific level. Let's look on Zi 1/2. What is Zi 1/2? Zi 1/2 is e to the power minus beta, 0 multiplied by ei, plus mu multiplied by 0. Why 0? Because, well, write it down. It's a sum of k from 0 to 1, e to the minus beta k ei minus mu k, right? This is the partition function of a level. This goes to e to the power minus beta, k is equals to 0, so it's 0 ei minus mu multiplied by 0 plus e to the power minus beta 1 multiplied by ei minus mu multiplied by 1. Eventually we obtain what? We obtain that z 1/2 equals to 1, this is simply 1, plus e to the minus beta ei minus mu, z I1/2. And if I want to calculate the occupational probabilities of level I, okay, Fi, the probability of level I1/2 to be occupied equals to what? It is the probability that there is one single particle, which is just this, e to the minus beta ei minus mu, divided by z. What is the z over here? We have 1 plus e to the minus beta ei minus mu. Okay? And it's equals to 1 divided by 1 plus e to the minus beta ei minus mu. Very simple. What is the probability of the level I1/2 not to be occupied, to be empty? I don't care about all the other levels, by the way. I only care about this level. What is the probability of this level not to be occupied? So it's simply 1 minus Fi. It's simply going to be 1 minus Fi. Okay, so, but this is for one single level, right? We have only one single level here. This is what I told you. Now, by factorization, I can now say what is the probability of level 1 to be occupied, level 2 not to be occupied, and level 3 to be occupied. Okay, what are those probabilities? It's simply F1/2 to be occupied multiplied, because of the factorization over there, multiplied by 1 minus F2/2 not to be occupied. So this is the probability of the second level not to be occupied, and the probability of the third level to be occupied. So this is F3/2. And I don't care about the spin downs. So the spin down levels can be either occupied or not occupied. You see, it's simply multiplication. The only thing that I need to do, is to compute the probabilities per level. And if I want the probability of the whole system, I just need to multiply them. Where it's going from? It's coming from here, because of the multiplication or the factorization of the partition function. Each state or each level is completely uncorrelated with all the different other levels. Okay, now that we have this, then we can say, well, instead of studying what happens to the whole system, I can study what happens to a single level. I can study the occupation numbers or the occupation fractions per level, because they are all very similar, all the three levels, and all different physical systems are going to be exactly like this. The only thing that I care about here, well, there are two parameters. or one parameter. The temperature, the EIs are constant. Okay, the EI is constant. So what can I play with? I can play with the beta, which is my temperature, and the chemical potential. Okay. So in order to see, well, this state is going to be, what is the probability of this state to be occupied? So the probability is it's something between 0 and 1. 0 is, well, probably it's not going to be occupied. 1, probably it's going to be occupied. And we want to see how this probability changes with the temperature and the chemical potential. Now the same is going to happen for all different other levels, right? Because it's the same function for all of them. It's simple multiplication. So for example, if everything is very close to 1, so the probability of each specific configurational state is also 1. So what I'm going to do now, I'm going to explore this function f, which I define it as 1 divided by e to the, I'm sorry, there's no minus. This is, you haven't noticed this, but there is no minus over here. This is a mistake. So, because I divided, I have taken out this factor and this factor out, and I have left only with this guys. So, f e beta e minus mu plus 1. I want to explore how this function behaves. So this is the occupation probability of a general level E. This is called a Fermi function. Fermi function. And I want to explore how this function behaves, as a function of a temperature, of the chemical potential, etc., etc. So first of all, I can ask you, well, what is the average number of particles for this system? Okay, I can ask you, what is an average? It's going to depend on this Fermi function. It's going to depend on this Fermi function. So how I'm usually computing some averages, again, there is a thermodynamic way and there is a statistical mechanics way. So the thermodynamics way, I would say, I know that e to the minus, or I have a psi, this is the grand canonical potential, it equals to 1 over beta log of z, okay? And from the representation of this psi, an average is going to be equals to the minus d psi to d mu. Okay? Because this is the mu is the associated variable with the number of particles, the average number of particles. But there is a much more convenient way. And this convenient way is basically saying, what is an average? What is an average? An average is a sum of all n's, of all i's, and all j's, okay, of what? So, if we're going to a specific, I is the different levels, energetic levels. J's are the different spins. So, specific I and specific J is looking on a level number I with spin number J. Now there are either 0 particles over there, no particles whatsoever, okay, or 1 particle over there. So what is the probability of having 0 particles? Is 1 minus Fi j. This is the probability of this guy not to be occupied, multiplied by the number of particles, so the 0. Because I'm calculating average. Average is different values of n multiplied by the probability to having this value of n. plus 1 multiplied Fij. Now, since Fij, Fi plus 1/2 of Fi minus 1/2 equals exactly to the same thing, this is simply a sum of over I Fi 1/2 because of the degeneracy. Okay, if we had some external magnetic field, the degeneracy would be broken. So this is 2 multiplied by, but I know what is Fi. This is this guy. I don't even care about the 1/2. So it is a sum of 1 divided 1 plus e to the minus beta, without minus, e to the beta ei minus mu. Okay, let's put it on top. This is the average n. We don't need to perform any derivatives. We need to count. You know what are the weights of different I goes from 1 to 3 of different values. We only need to count. The same goes for the average energy. The moment you know the partition function, you count all different possibilities, all different configurational states, and you're done. Very, very simple. Instead of taking some derivatives, etc., etc., etc. Count. Just count. And at some point, we're going to replace the counting procedure by integration procedure, as we already have done before for the Debye model. Alright, so if I want to explore average n, if I want to explore average energy, what is going to be average energy? Average energy, U, is going to be equals exactly to the same thing. It's 2 to the sum of I goes from 1 to 3. Okay? And here I would have EI multiplied by 1 divided by plus beta EI minus mu. Okay? It's exactly the same procedure, it's just here I'm going to multiply instead of 1 by EI. That's it. Now you see everywhere appears this Fermi function. Here and here. So in order to explore the averages, in order to explore the probabilities, everything, it's eventually dependent on the Fermi function. We define it over here. So if I know how this function behaves, I know everything about the system. Maybe it would be hard to compute something, maybe the summation is going to be hard, but this is just a simple sum. You can always do it numerically, for example. But instead of doing it numerically, let's study qualitatively how this guy behaves. Now, interesting enough, the same function appears in something that looks like a very distinct field from physics, and it's artificial intelligence, for example. Okay. So if you would look on, so how usually artificial intelligence is built? It's built on the top of a neural network. And there are some specific neurons. Each neuron is deciding either to fire or not to fire. In an artificial intelligence, well, it has a lot of inputs, and it decides if to get out 0 or 1. The function that is used in order to decide what is going to be the output of a single neuron in all this big neuronal network is exactly the same function, the Fermi function over here. And why it's like this, the origins are very, very similar to the physics of Fermi systems. It's a logistic function or logistic description of cloud information. Well, it's not in this class, but you can see that the same tools that we are using in physics are actually appearing and rediscovered in, well, not discovered, they are inspired in other completely different fields. Why? Because the only thing you care about here in statistical mechanics, it's about statistics and occupations. The same goes for artificial intelligence or neural networks, search algorithms. Very, very general tools. Okay. So let's study this guy. How it behaves. Well, it's actually going to be dependent on mu. So if we have, let's plot over here. So let's plot how it's behaving as a function of E divided by mu. And here I'm plotting my f. So what is E divided by mu? So it's 1 divided by 1 plus E beta mu we should have outside, and here we have E divided by mu minus 1. This is our function. Now, it's restricted between two values. What is the minimal value that this guy can obtain? 0, right? It's always positive. And the limit when E divided by mu is very, very, very large, so it's 1 divided by 1 plus something very, very, very big. So expect always for this guy to decrease to some 0. No matter what, it will always decrease eventually to 0. Okay? For the values of E divided by mu goes to something big and negative, what we have over here, 1 divided by 1 plus 0. So the maximum value of the Fermi function is 1. So we can always place f between 1 and 0. We'll see what actually this 1/2 is. Okay. Now, the shape of this function is going to be very different dependent on what is mu with respect to kbt. Okay. What is mu with respect to beta? So if mu is, for example, simply kbt, so it's equals to beta, this guy it's, well, it's doing something like this. Yeah. It's not exactly linear, well, but you get the point. So it's something like this, and this is this guy, mu equals k Boltzmann T. Now, let's increase mu. Mu is some sort of an energy, right? Let's increase the energy. What happens there? If we increase the energy a little bit, let's, for example, go to 4k Boltzmann T. Okay, so this guy is mu equals 4k Boltzmann T. Okay. Let's increase it a little bit more to what? Let's take 10k Boltzmann T. Okay, so this is mu equals 10k Boltzmann T. And we can continue even more by increasing this energy, the energy of the potential energy. Eventually we will get almost a step function in the very, very high temperature. The nice thing about this is that all of those curves cross each other exactly where? Exactly at 1/2. Okay, and where this 1/2 is located is exactly when E divided by mu equals 1. Okay, and this is clear for the formula, because when E divided by mu equals 1, so we have 1 divided by 1 plus E to the power 0, which is 1, it's always should be equals 1/2. So what happens here? What do we have here in this plot with a lot of curves? So if the temperature mu is very low, if mu is very, very low, okay, so we have a spread of occupation. Okay? You can say, well, if the chemical potential is low, or the temperature is low, I'm sorry, if the temperature is low, then you, mu is low, you can have states, partially occupied states are lower energies and higher energies. The more you increase mu, you can say, when you actually, mu is constant. Think about it in this following function. So mu is constant in our perspective. What you can play with is the temperature of the system. You're saying, what is my temperature? So when you increase the temperature, the probability distribution of occupation of a specific state becomes very broad. You can occupy the energy, well, there is always better to be at lower energies, but even states with higher energies are occupied, okay, for a high enough temperature. Now, when we increase when we start to decrease the temperature, mu becomes higher and higher than the regular K Boltzmann T. It can be 4 K Boltzmann 3, 10 K Boltzmann T, etc. What happens when we start to decrease the temperature? We see that the lower energy states are much more occupied than the higher energy states. So the system tends to first occupy the lower states, and there's also some small probability to be occupied for the higher energy states. We can continue decreasing the temperature even more, okay, to 10 when mu is now equals to 10 K Boltzmann T or 100 K Boltzmann T, and what we see, there is a transition. What is the transition? The transition is that for very low temperatures, the fermionic system, is occupying, there is the F Fermi function is a step function. Okay? It's strictly 1 up to the energy level, which equals exactly to mu. Okay? And it's strictly 0 for all the energies or the energy levels that have energies which is larger than mu. Okay? So for T goes to 0, E smaller than mu, occupied, and F equals 1, E larger than mu, empty, and F equals 0. So this is what we expect, or we've been told all the time, that only the lower energies are occupied. The thermal fluctuations, what they do, as I increase the temperature, those thermal fluctuations, they actually permit the particles also to go and occupy the energy levels that are much more higher in the spectrum. But when I decrease the temperature, everything collapses to only to the lower energies. So usually this mu, it's also called mu Fermi, mu F, mu Fermi. Sometimes it's also called E Fermi. and it symbolizes the energy or the maximal energetic level that it's going to be occupied at a zero temperature limit. At zero temperature for fermionic system, non-interacting fermionic system, it's called a Fermi fluid. Okay? At zero temperature, what we are going to see is all the lower levels are occupied and all the higher levels are unoccupied. And this is all we can obtain only by looking on the Fermi function. Now, what actually happens is when we constructed this, or when we constructed the average n over here, we assume that mu is constant and the average number of the particles is constant. Now we can do it a little bit backward. We can say, if we know what is the average number of the particles, let's find mu. Okay? Because we can actually find mu from the average number of particles, and we can say, what is mu with respect to the temperature? And it will tell us either the distribution goes like this in a flat fashion, or either it's behaving as a step function. Okay? So what we can do, and this is the usual trick, we can say, well, we use the grand canonical ensemble in order to, and we had a constant n, a constant mu, and constant t. In reality, usually we have constant number of particles. What we are going to do now, we're going to represent the average number of particles, n, and calculate mu as a function of n. Okay? So what I'm saying here is the way to calculate what is this mu Fermi, what is this E Fermi for a system, how it behaves as a function of the temperature and the average number of the particles, is basically to state the following thing. N average, we already know, it equals to 2 divided by E beta E1 minus mu, plus 2 divided by E beta E2 minus mu, plus 2 divided by e to the power of beta E3 minus mu. Little kids. Okay. Now, what I want to do, usually I'm saying beta, someone should tell me what beta is, and mu, somebody should tell me what mu is, because those are the properties of the reservoir, and then I can define the average n. I want to do this thing the other way around. I'm saying, well, let's assume that I know what n is and what beta is, and I want to find mu. Why? Because this is the usual situation in the physical system. So in the physical system, it's really hard for me to appreciate what is the chemical potential of the reservoir. I don't really know it. Now, if I don't know it, I don't know how to actually say what is this E Fermi of my system. I can know how many particles, or what is the density of the particle, the average density of the particles. This is usually what I do know. Right? I'm looking on the current of the electrons in the system. I can assume that I know that each electron is associated with some atom or an ion. I do know what is the density of the material, so I know how many atoms I have there. So I should know on average what is the number of particles that I have in my system. But how? And I know what is the temperature because, well, I can control the temperature. I usually do not, I cannot control the chemical potential. Okay? But by knowing this guy and knowing this guy, I can approximate, not approximate, but I can calculate using this formula. It's already, of course, it's some crazy formula to take mu out of here, but basically it can be done. Okay, I know the different energies, right? So what I know is by knowing n and beta, I can obtain some knowledge about mu, and if I know mu, I can say something about how my fermionic levels are distributed. Okay? I can afterwards play with the temperature and say what is going to happen as a function of temperature. It is going to be occupied only the lower levels. Is a specific level with energy equals to something, it is going to be occupied. What is the probability of it to be occupied? Okay. So I need to compute mu. Usually I don't know it. I know the average n. And the way I'm doing it is by taking this as a constant, beta as a constant, and computing mu as a function of n and beta. Now, as you see, it's usually easier said than done. Easier said than done. But let's assume what happens here in the limit when t goes to 0. Right? T goes to 0, and let's also assume that E1 equals to E2. Okay, so what happens in this limit? First of all, in this limit, 1 e to the power beta e minus mu plus 1 has two values. So it either we have e larger than mu and e smaller than mu. So for this guy, it's either e to the power minus beta mu, right? Am I right? What I have epsilon minus mu, I'm sorry. E minus mu, or 1 plus e to the minus beta e minus mu. Okay, so I'm having two limits. Either this guy is big or either this guy is small. Right? And then the temperature goes to 0 limit, or basically beta is very, very large. Beta is very, very large, so I have those two limits. Okay, when I'm using this approximation, and also assuming that E1 equals to E2, what I obtain that n equals to 2 divided by, or I will have here 4 divided by e to the power beta e1 minus mu plus 2 divided by e to the beta e3 minus mu. Okay. I am going to use this value, so I'm assuming that mu is somewhere between E1 and E2. Okay, this is what I'm going to assume. So if mu is somewhere between E1 and it's E3. So mu is larger than E1 and it's smaller than E3. Okay, because E3 is the maximal level, E1 is the lower level, and I'm assuming that only the lower levels are going to be occupied in a very, very, very low temperature limit. So what I'm getting here, I'm getting that the average n equals to, so here E1 is smaller than mu, so here I will have 4 multiplied by 1 plus e to the power plus 1 e to the power beta E1 minus mu. Okay. And here I'm going to have plus 2 multiplied to the power of e to the minus beta E3 minus mu. Now what I'm doing next, Next, I'm saying what is the average number of the particles? What is the average number of the particles? Let's see what I have done here. The average number of the particles is, if I have n, well, I don't really know because it depends on how many levels I have over here. But let's assume that I know what is the average number of a particle because I can control it. Okay? This is something that I can control from the outside. And I'm saying if the average number of the particles is 4, why 4? Because otherwise I cannot solve this equation. You see? It equals to 4 plus 4e to the power of beta E1 minus mu plus 2 e to the power of minus beta E3 minus mu. Okay? I cancel this force out and I'm getting so here this is 1 minus, I'm sorry, this is 1 minus and then I will get 1 minus. Okay, this is good. And I'm getting 4, this is minus 2, 4 to the power e beta E1 minus mu equals 2e minus beta E3 minus mu. Now this guy I can already solve because, well, it's 2 and 1 over here. I'm running out of time. But what I'm getting from this is that mu equals E1 plus E3 divided by 2 plus K Boltzmann T 1/2 K Boltzmann T log of 2. So you see that mu is actually sitting exactly, so if we plot this, and those are the different energies. So this is E1 and this is E3. So the degeneracy of E3 is degeneracy is D equals 2. It can be the spin up and spin down. And the degeneracy of E1 is D equals 4 because it can have spin up, spin down, and E1 equals exactly to E2. We know that mu here is the middle point between those two states. This is E1 plus E3 divided by 2. And we know that for our choice, we got mu somewhere over here. This is mu. You can call it mu Fermi. What it basically means? It means that for the lower temperature, very low temperature, we're going to obtain a step function. So F E divided by mu or simply F is 1 till what? Till mu Fermi, and 0 for all energy that is above mu Fermi. What we are getting for low energies, E1 and all its degenerative levels are going to be occupied. Okay, this is over here. So all the levels below mu Fermi or E Fermi, whatever we call it, are occupied. All the levels above are unoccupied. as we increase the temperature of the system, we will have a slip of the occupation probability to higher levels. Okay. And what you will learn in solid state, in a solid state class, is that exactly those electrons that are slipping outside of the E Fermi are the conducting electrons that are used everywhere are the conducting electrons. And how many of them, and what is the current, etc., is all defined by the presence of the E Fermi and how well you are above it. So there are possible fluctuations to higher level spectrum for finite temperatures, but in a very low temperature regime, we will see that only lower energies are occupied, everything else is unoccupied. And there is a transition between those two states. Okay, we will finish here and we'll continue more with Fermi and boson statistics next week.